Dear students, after studying this module, you shall be able to know what are aromatic nucleophilic substitution reactions, learn about the mechanism of SRN1 reaction, identify kinetics and suitable substrates for SRN1 reactions, evaluate the factors affecting nucleophilic aromatic substitution reactions, or in short SRN1 reactions, analyze factors governing suitability of reaction conditions for SRN1 reactions, or to say nucleophilic aromatic substitution reactions. Now let us introduce this topic of SRN1 reactions. Nucleophilic substitution reaction occurs when the substrate, either aliphatic or aromatic, is attacked by a nucleophile with the removal of a leaving group. In this module, we shall be discussing or focusing on aromatic nucleophilic substitution reactions with particular emphasis on SRN1 mechanisms and the factors which affect the rate of these reactions, like the substrate structure, leaving group and attacking nucleophile. We will discuss the factors very briefly in this. However, we will discuss the mechanism in detail and the factors will be taken up in detail in the next module. The SRN1 reaction, that is, which stands for substitution radical nucleophilic unimolecular reaction, is defined by a unimolecular nucleophilic substitution reaction which involve radical anions. The SRN1 reaction was discovered by accident when a strange anomaly in the alkylation of aliphatic nitro compounds by alkyl halides was observed. In 1949, Haas et al. Performed a routine alkylation of 2-nitropropane with 4-nitrobenzyl chloride. The product obtained was mainly the C-alkylated compound A. Now this compound A is shown to you here, which is a C-alkylated compound by reaction of 4-nitrobenzyl chloride with 2-nitropropane. Due to the involvement of radical anions, the SRN1 reactions may occur via a chain or a non-chain mechanism. This reaction type was discovered in 1970 by Bunnett and Kim. The IUPAC has given the designation for these kind of reactions as T plus DN plus AN. It has been reported that the SRN1 reaction mechanism or the chain mechanism is initiated by single electron transfer, or we will abbreviate it as SET transfer, from a chemical catalyst. As you know, catalyst, I like to reiterate again, they increase the rate of reaction without the participation of themselves in the reaction, or from a external electronic source to the substrate which produces a radical anion. That is, SET occurs from a chemical catalyst or from an external electron source. The general schematic representation for SRN1 reaction is shown here to you. Now you can see here, as normal radical reactions they proceed, the first step is the initiation reaction, the second is the propagation, and third is the overall reaction. As depicted in this figure, in the SRN1 mechanism, the initial attack takes place via an electron donor rather than a nucleophile. The radical anion thus formed leads to the removal of the leaving group and left behind a radical available for attack by the incoming nucleophile. Specifically, for aromatic substrates, the reaction go by sign substitution, although the need for electron withdrawing groups is not that stringent for these reactions. Interestingly, students, the involvement of radicals allows a chain mechanism for SRN1 reactions. A chain mechanism is a self-sustaining reaction whereby, as you know, the reaction continues by the formation of reactive intermediates that recycle during product formation. These intermediates then react to continue additional processes, keeping the continuity of the reaction intact. Now, being a chain reaction, this mechanism follows, like I told you, the initiation step, the propagation step and the termination step. Now, this is shown to you here in the specific example of this benzene ring. Here is the SRN1 reaction with aryl halide as the substrate. Now, as you can see in this figure, students, the aryl halide, which is numbered as 1, first accepts an electron from a donor and becomes an anion radical, which is numbered as 2, which loses the halide anion, giving rise to aryl radical 3, which can be easily attacked by the nucleophile 4 to form a new radical anion 5, which subsequently leads to the product formation, which is numbered 6. During the chain propagation step, the radical which attached nucleophile gets recycled to give intermediate radical, which was numbered 3 initially, which can also abstract a proton from the alternate RH species 7 to form the product 8 and leading to chain termination. The mechanism looks complicated and initially discovered through a very interesting observation, which are as follows, and I am going to discuss it with you. When 5-iodo-1,2,4-trimethylbenzene was treated with a strong base such as potassium amide, that is NH2K, it is represented as this. It is a potassium salt of amine in the presence of ammonia. Two products were formed in the ratio of 0.63:1. By the time benzyne mechanisms were known and based on sign substitution, strong base and relatively less reactive substrate, this reaction was expected to go by this benzyne mechanism. However, benzyne mechanism would have led to product formation in equal ratio, that is 1:1. But this is not the case here, as the product ratio is 0.63:1. Now you can see this reaction over here, we have drawn it for you. Therefore, the reaction was suspected to go by a different mechanism. A radical mechanism was proposed for this reaction. The involvement of a radical mechanism was further confirmed by addition of a radical scavenger that leads to different product ratios. Now you can understand, along with this, the rejection of benzyne mechanism, we have here taught you the proof of the new radical mechanism, that is the SRN1 reaction mechanism. To explain the IDO result, it has been proposed that in addition to the benzyne mechanism, a free radical mechanism is also operative here. Now this proceeds as follows, which is the free radical mechanism in SRN1 reaction of 5-iodo-1,2,4-trimethylbenzene. Additionally, it was discovered that the SRN1 reaction can occur via a non-chain mechanism as well. Non-chain SRN1 reactions are less known. Non-chain SRN1 reactions also occur in solvent cages, which are defined as a region of space which includes the reactive species surrounded by solvent molecules. The solvent cage restricts the movement of reactive intermediates, thereby not allowing the propagation, while stepwise substitution occurs, giving rise to product formation only. Example of non-chain SRN1 reaction. Now students, as you can see that earlier we have discussed, that is chain radical mechanism. Now we will here discuss the non-chain SRN1 reaction mechanism. Now here you see that this is an example of non-chain SRN1 reaction, where the solvent cage does not allow the propagation of this reactive intermediate, thus only leading to product formation and not further leading to any other reaction, that is a side reaction, or giving rise to any other different product than the whole and sole one product only. The substitution of iodo group with the incoming reactive nucleophile occurs via a non-chain SRN1 reaction here. A number of useful reactions proceed via this mechanism, including photostimulation reactions, electrochemical reactions, and even more so, no chemical reactions such as reaction of benzyl chloride and nitrobenzene. Initiation can also be achieved by a number of methods. The most commonly used being is the photostimulation, introduction of solvated electrons, or thermal reactions are an example of initiation. Now we will discuss about the reactions which are particularly involving the SRN1 mechanism. As an example of photostimulated reaction, as I told you above, the reactant 3-chlorophenyl trimethyl ammonium iodide upon reaction with trimethyl tin sodium, that is 1, proceeded efficiently, that is in 30 minutes, to give you 1,3-bis trimethyl stenyl benzene in good yield of 85%. Now this reaction, you can see here, it is a photostimulated reaction, and you can see how this particular product, that is bis trimethyl stenyl benzene, is obtained in good yield using the photostimulated reaction. Interestingly, the reaction was very slow in dark conditions and completely quenched upon addition of para-nitrobenzene, that is PDNB, and a concentration of 20%, a well-known inhibitor of the radical anions. Thus, here in this case you can say that if the reaction is totally quenched upon the addition of PDNP, thus unambiguously this establishes the presence of SRN1 chain radical mechanism allowed by spontaneous electron transfer, that is SET, which was stimulated by photoradiation or by simple irradiation of the light. Now you can see this here, the different sets of conditions which we have put to this substrate. Let us see, if we have photo irradiated it, then it takes only 30 minutes and the yield is 85%. However, if we have irradiated it again for 5 minutes, the yield is 55%. So notice the time of irradiation is also important here. When you increase the irradiation time by 25 minutes, that is the 5 times from 5 minutes to 30 minutes, or 6 times I would say, the reaction yield increases from 55 to 85%. However, students, look at how much the yield decreases when the reaction is done in dark. For even 30 minutes, the yield is only a meager 10%. Now, if the reaction is done in dark along with the quencher of the radical anions, which is PDNB 20%, again the reaction is done for the same duration, that is 30 minutes, the yield is 0%. Now you can say clearly that this mechanism involved in this particular reaction is the SRN1 chain reaction. A number of aromatic heterocyclic systems undergo reactions via SRN1 mechanisms. Let us see a few examples here. Now you can see that trimethyl benzene substituted with bromine along with the 2-methyl pyridine, it gives you this product on photoirradiation in 87% of yield. Next example is this one, you can see here, and there are various examples that we have shown here which are good examples of SRN1 reactions. Some of them are performed by photoirradiation, some of them are also performed in dark, but since the promotion of radical anions, the promoter is there, that is liquid ammonia in this case, as you see, that is the 3-bromothiophene, in which you can see the reaction has taken place because of the promoter of radical anions, that is liquid ammonia. Then again there are very nice examples of aromatic heterocyclic systems undergoing the reaction via SRN1 mechanisms. The lithium salt of 2-nitropropane reacts with dinitrocumene to afford a 87% yield of the substituted product within 3 hours. Now you can see here the 87% yield, that is a very high yield when lithium salt of 2-nitropropane reacts with dinitrocumene, and this product is formed in 87% yield only in 3 hours. Now this is actually explained only by radical mechanism, whereby radicals are regenerated to complete the reaction and to give you a very high yield, that is supporting the SRN1 mechanism. The nucleophile initiates its substitution in dihaloarenes. Now you can see here clearly it is shown, goes very well by a variety of nucleophiles including ketone enolates, aromatic thiolates and dialkyl phosphides. Now you can see here double SRN1 reaction takes place because there are 2 leaving groups, 2 ido groups. So obviously the double SRN1 reaction will take place and both will get substituted by this particular group. This is having the active methylene group, so potassium salt of this active methylene group is there to give you the product. Symmetric and asymmetric biaryls can also be synthesized by the electron transfer, that is the SET, the SRN1 mechanism, through the substitution of a haloaromatic substrate by beta-naphthyl nucleophile such as the anion of 2-naphthol and 2-naphthylamine. Now you can see here when this is irradiated by using the ammonia and the light, this particular reaction gets transformed into the products. The electrochemical reduction of aryl azosulfides yields the corresponding sulfides and decomposition products. Now you can see here this cascade of reaction giving you an example of chain SRN1 mechanism, which is operative in all the examples that we have discussed, except for that one example of non-chain SRN1 reaction. The reaction of 1,2-dibromotetrafluoroethane with thiophenoxides in the presence of catalytic amount of SO2 proceeds via SRN1 mechanism. Specifically students, the presence of sulfur dioxide in the reaction promotes a SRN1 process which results in quantitative yields of the ArSCF2CF2Br without the byproduct, which is the ArSCF2CF2H, which is the non-brominated product. Now you can see here how the sulfur dioxide is acting as the generator of the radical anions, and thus it gives rise to the SRN1 reaction mechanism with only the catalytic amount of it. Now students, let us summarize this module for you. In this module, we basically covered the SRN1 mechanism and some factors which are affecting it. Not only did we cover the chain mechanism, we also covered the non-chain SRN1 mechanism. Now beginning with the summary, radical nucleophilic aromatic substitution or SRN1 reactions involve substitution on an aromatic compound mediated through a nucleophile and an intermediary free radical species. Now understanding this concept, that is SRN1 reaction, it goes through a free radical species which acts as an intermediate, and this process of SRN1 reaction also follows all the steps which are involved in the free radical generation. The reaction, that is the SRN1 reaction, we taught you, is usually performed in either liquid ammonia or dipolar aprotic solvents such as dimethyl sulfoxide or hexamethyl phosphoric acids. Now these solvents students, that is the liquid ammonia or the dipolar aprotic solvents such as dimethyl sulfoxide or hexamethyl phosphoric acid, they promote the formation of radicals and thus are ideal solvents for the SRN1 chain reaction mechanism. Next we taught you that the reaction rates are significantly lowered by the presence of small amounts of a radical inhibitor such as para-dinitrobenzene. Now, if you reminisce, we have used 20% para-dinitrobenzene and that acted as an inhibitor of the free radical formation. And if you remember that reaction in which we carried out in dark for 30 minutes and with the use of para-dinitrobenzene, the yield of the product was 0%. This further supports the free radical mechanism that is involved in SRN1 reactions. Thus, it gives way to the benzene mechanisms which were already known at that time when these new reactions were discovered and the byproducts and their ratios was discovered and they were studied. The SRN1 reactions are synthetically useful as they form new carbon-carbon or carbon heteroatom bonds between sterically hindered carbon in good yields. Now students, if you remember that we have taken numerous examples where we have taken up the carbon-carbon and carbon heteroatom bonds and their formation through the SRN1 reaction. Unlike the SNAR mechanism that requires suitably substituted substrates and the benzene mechanism which requires strong basic conditions, the SRN1 reaction mechanisms on the contrary, they proceed under relatively milder conditions and they give you conveniently good yields. Now as you saw that photo-irradiated reactions gave you as high as 85% of the product in just a span of 30 minutes. Initiation of SRN1 reactions can be achieved by a number of methods, the most commonly used being photostimulation, introduction of solvated electrons or thermal reactions. Now these all promote the formation of radicals, thus initiation is promoted by these factors. In general students, we have taught you that aromatic nucleophilic substitution reactions, they require a good nucleophile such as the one carrying oxygen, nitrogen or cyanide group. Second, a good leaving group such as halides, out of which the best leaving group is the iodine followed by bromide, chloride, and the least favorable is the fluoride. Electron withdrawing substituents on the benzene ring, they preferably also are good for the reaction such as the carbonyl group, the nitro group or the cyanide groups which are located at ortho or para positions to the initial leaving group which is there in the reactant. Now students, I hope that studying these factors as well as the non-chain and chain SRN1 reaction mechanisms would have given you a good insight of how different reaction proceeds in different reaction conditions, and one reaction mechanism already known might not be suitable or applicable for any other reaction which is newly discovered or found. This is what makes chemistry a very fascinating subject. So I hope you found this module very, very informative.